we have this new mathematical idea of a vector field, but every time you have a new mathematical idea, it's helpful to think about, the real world and think about where does this new mathematical idea show up in the real world. Well, one place that this idea of a vector field shows up in the real world is the motivating example for the vector field, which is this velocity field of the velocity of bits of debris floating around the surface of a pond. So anytime you have a fluid that is flowing around, the velocity of that fluid can vary from place to place, and so that velocity is a vector field. So that's maybe one of the most important examples of how vector fields show up. Another example of how a vector field can show up is a force field. So many forces can be described as functions of location. So for example, if you think about the sun if we put the origin of a coordinate system at the center of the sun is sitting at the origin. Well, the force of gravity from the sun is a vector field, right, that exerts force on any object that is within the gravitational influence of the sun. So because the force varies as you move around space, right, when you get further from the sun it gets weaker, when you get closer to the sun it gets stronger. Because the force varies as you move around space, that means we have a different vector for every location in space, and that means that it's a vector field. So a force field is a common example. I've drawn it as if this is two-dimensional, but of course gravity happens in 3 dimensions and not 2. Another example of a vector field out in the wild is the electric field. So the electric field is similar to a force field, but the electric field isn't actually a force, or doesn't produce a force. The vector that the electric field produces is not a force. So for example, if we put a positively charged particle at the origin and fix it there somehow, it produces a vector field called the electric field that points away from this charged particle. The further you get from the charged particle, the weaker the electric field is, and so the vectors get shorter. And the closer you are to the charged particle, the stronger the electric field is, so the longer the vectors are. Now we're used to thinking of the electric force as producing forces, so why did I say this isn't a force? Well, to get a force out of this, you have to have another charge, right? So if we put a little charged particle out here somewhere, if we make it positively charged, it turns out that the force from the electric field is the electric field, which E is one symbol for the electric field, times the charge of your charged particle. Right? A positive particle has a positive charge, so we take the electric field value at this spot and multiply it by the positive charge, and so we get a vector pointing that way. On the other hand, if we put a negative particle, or a negatively charged particle at some spot, well, the electric field itself is pointing away from the origin in this situation, but because we're multiplying it by a negative charge, that means that the force that this particle experiences is actually pointing towards the origin instead of away from it, which is why opposites attract in electromagnetism. The final example of a vector field in the wild is a gradient. So this is something that I mentioned when we were looking at SAGE. If you have a function, you can get the gradient vector field in SAGE just by calling dot gradient. So anytime you have, right, the gradient produces a vector, because remember the gradient of a function f is partial f partial x comma partial f partial y. Both of these are functions of x and y, right? This partial f partial x, this is really shorthand for partial f partial x of x comma y, and same thing for partial f partial y. So these are both functions of x and y, and they're packaged up in a vector, and so the gradient has two inputs in this situation and two outputs, and so it's a vector field. And indeed, we've plotted the gradient as a vector field even before we had the vocabulary of a vector field. So we have several sources, both mathematical sources and real-world examples of how vector fields show up. Given all of these ways that vector fields show up, maybe one thing we should think about is, what are the sorts of things that we might want to, the questions we might want to ask about vector fields, or the things we might be able to measure about vector fields? If we think about the velocity field example of a vector field, right? If we're thinking about debris floating around on the surface of a pond, if you're looking at this vector field, you might want to ask, well, what is the actual path that a particle would follow, right? If I dropped a bit, if this is how the fluid is flowing around the surface of the pond, and I drop a leaf into this pond right here, the leaf is going to follow the vector field around, because remember, the vectors are representing a velocity. So right, the leaf is going to go this way and then curve down like this and then swoop over this way, I guess, and slow down a lot. And then it gets hard to know what happens in the middle here. So how would we solve that kind of problem? Well, if we had the position of the particle, right, that would be a function of time, so we could call that r of t. Well, the rate of change of that position would need to be equal to the vector field, right? Because the velocity of the leaf should be equal to the velocity of the water that the leaf is sitting in. So r prime should be equal to f of r of t, like this, right? So the velocity at time t is equal to the velocity of the water at the position at time t. But if we write out what r of t really is, right, it's an x-coordinate function and a y-coordinate function, then r prime is x prime of t, comma, y prime of t. Okay, f itself, remember f is a function of x and y, and let's write it with coordinates function m and n. Okay, then what we have here, this equation that we wrote down right here, if we compare x coordinates, it's saying that x prime of t has to be equal to m of x of t, comma, y of t. And looking at y coordinates, I'm missing a prime here. Looking at y coordinates, it says that y prime of t equals n of x of t, y of t. Well, this is a system of differential equations, right? Because each of these equations has a derivative on one side and the undifferentiated function on the right side. So these are differential equations. This is an interesting problem, but this is not a problem we will spend any time solving, because if you want to solve differential equations, you should take a differential equations class. So this is a good question, but let's forget about it for now. Another question we could ask about a vector field is, does a fluid flow out of a point or into a point, right? So you can imagine that at this spot right here, for example, if we look at the region nearby, it looks like the arrows flowing into this spot are a little bit longer on average than the arrows flowing out of this spot. And that means that at this spot, in total, fluid is flowing in. That's in contrast to, say, this point over here, where if we look at all of the vector field nearby, the vectors flowing out of this spot are on average a little bit longer than the vectors flowing into this spot. So for this point, fluid is in general flowing out. It might be nice to have some way of calculating for each spot, given a vector field, for each spot in the plane, whether the vector field is in general flowing out of a point, out of that point, or into that point. In fact, maybe we could even attach some number that tells you how much fluid is flowing into the point or out of the point. That would be an interesting thing to measure. Another thing we could measure is how fluid rotates around a point. So for example, let's see, if we look down here, the vectors below this point are pointing to the left a little bit more on average than the vectors above this point are pointing to the right. And so that means that at this point, this vector field is on average kind of turning this way. Sorry, I misspoke. The vectors below are pointing to the left and the vectors above are pointing to the right. So both of these, the vectors above and below, are contributing to this rotation clockwise around this circle. So it looks like the vector field is kind of turning around this point a little bit. That's very different than, say, over at this point, where if we look at the nearby vectors, above it's pointing about like this, below it's pointing about like this, to the right it's pointing about like this, to the left it's pointing about like this. Well, these, if we think about how these four vectors are trying to rotate around this point, they all kind of balance. The two that go through the middle of this point, they don't contribute any rotation because they're going through the middle. But the one above and the below, they do contribute rotation, but since they're trying to rotate in opposite directions, they kind of cancel each other out. So we might want to compute some number that characterizes for every point in the plane, how is the vector field rotating around this point. Right? So these are some interesting kind of fluid flow examples of questions we might want to answer, or things we might want to calculate. If we think of this vector field as a force field, well then things get even more interesting, because we might want to, for some vector field, we might want to ask, as an object moves along a curve, say maybe like this, we might want to ask, how much work does the force do on this object? For this particular path, right, this particular path sort of closes up on itself. Well, along the first portion of this path, right, up to about here maybe, these force vectors are pointing in the direction of motion, roughly speaking, not totally, but roughly speaking. And when the force is in the direction of motion, that's positive work. So the force field is doing work on the object. But then in this portion of the trip around this loop, now the force vectors are pointed against the direction of motion, and so that's negative work. And so the object is doing work on the force field, or the force field is doing negative work on the object. And maybe it would be possible to calculate what the total work around a loop like this is. That might be an interesting question to ask about vector fields. So you can see now that we have this new idea for a new type of function, a vector field, we have a whole new collection of problems that we have to deal with when it comes to calculating things or understanding things about vector fields.